Hi, everyone. We're going to get started in just a minute or two. We're just letting everybody in, and we'll start shortly. Okay, I think we can. I think we can get started. Welcome. I'm Ana Diaz-Rue, and I'm here at the Drexel Urban Health Collaborative and with the Drexel Center on Extreme Weather and Urban Health. And I'm delighted to welcome you to this webinar. This is fortunately the last webinar of our series with the center. We hope to continue this in the future, so keep in touch. But today we're very happy to have a very special webinar because we are actually going to hear from our research center's research project, which is a very important component of the center, which, as you can see on the slide, focuses on neighborhood heterogeneity and heat mortality impacts across cities of the Americas. And we have two great speakers and wonderful team members of CCUH and also the Drexel Urban Health Collaborative. And they are Usama Bilal. Usama is an associate professor here in the Department of Epidemiology and Biostatistics, and he's co-director of the Urban Health Collaborative and also of the Center on Extreme Weather and Urban Health. And Usama's primary research interest is in the macrosocial determinants of health, with a special focus on describing health inequities in urban environments, specifically urban health in Latin American cities and unequal effects of climate change on urban health, as well as policy modifiers of these effects. Um, and we also have as a second speaker, Josiah Kephart, who is an assistant professor in the Department of Environmental and Occupational Health at the Urban Health Collaborative. Josiah is also a team member of CCUH and the Urban Health Collaborative. He is an environmental epidemiologist who looks at understanding and mitigating the environmental determinants of health disparities. And after working for a number of years in community health, he received his training at the Johns Hopkins School of Hygiene and Public Health. And his research focuses on understanding the contribution of climate change, air pollution, and the urban environment to health disparities in Latin America and the US. And so interpretation, as usual, we have interpretation to Spanish and Portuguese. As part of the webinar, you can enable it using the interpretation button on the Zoom toolbar, and please submit questions using the Q&A button in the toolbar, and we'll be answering as many questions as we can at the end. And I'll just turn it over to Usama and Josiah to get us going with this presentation.
Hi, everyone. It's great to be here. I'm going to kick us off here. So my name is Josiah Kephart. I'm at the Urban Health Collaborative. And today, along with my colleague Usama, we're going to be talking about neighborhood heterogeneity and heat mortality impacts across cities of the Americas. So I'm going to get us started with a little bit of scientific background of the problem, and then Usama is going to talk a little bit about the center and start talking about some of the findings from the center's research project. So extreme temperatures are the most health-damaging weather hazard, and in fact, in the United States at least, contribute more to health or more to mortality specifically than all other weather hazards combined. So that includes things like droughts, natural disasters, hurricanes. Extreme temperatures are by far the biggest weather-related hazard in the US. And of course, we know that because of anthropogenic climate change, temperatures are rising and heat is becoming more common. So this means that extreme heat events are becoming more frequent, more intense, meaning the temperatures are hotter, and also longer lasting. We have more and more periods of heat waves where we have these long heat events of this persistent extreme heat, which really can have an impact on health. And so cities are really the critical environment for heat health risks. This is the focal point of environments where we're worried about heat health risks. And I'm going to tell you a little bit more. So why focus on cities? Well, first of all, 80% of the global population lives in cities. So if we're thinking about public health and where people are experiencing heat or where they live, a large majority of them live in cities. And this is also true in the United States, which has a similar, around 70, 80% of people actually live in urban areas. And the urban areas are particularly important when we think about heat because of the urban heat island effect. You can see this little graphic on the right. And in the urban heat island effect, heat from the sun gets trapped within buildings and streets. And so downtown temperatures in an urban core can be as much as 8 or 10 degrees Fahrenheit hotter than temperatures in the surrounding areas. There are also a lot of human activities like industry or vehicles that produce heat themselves, right? And so cities are hotter than surrounding areas. So if we're worried about heat, we're really thinking a lot about cities. Now, of course, these pockets of heat are not necessarily distributed evenly across the city. They tend to be downtown areas tend to be hotter, but even if you think about residential neighborhoods, there are a lot of different characteristics of the neighborhood built environment that can determine which neighborhoods are hotter and which neighborhoods are cooler. And so apart from where these heat islands are in the city, we also know, of course, that cities tend to have pockets of social segregation, where different neighborhoods have different social inequalities. And so these social inequalities can sort of interacting with these heat islands to determine which neighborhoods are at high risk for heat and which neighborhoods are at lower risk for experiencing health impacts from heat. And so what we've seen, previously did a study of 326 Latin American cities looking at heat and mortality at the city level, and we found widely varying heat mortality impacts across different cities. When we think about heat and health, this is a very context-specific problem. It changes quite a lot from city to city. And you can see here an example. These are figures. Perhaps you've seen these before, perhaps not. But on the x-axis here, we have the average daily temperature. This is in Celsius. And on the y-axis, we have the relative risk of death on a day with that temperature. And you can see here, for example, these kind of moderate temperatures in the middle tend to have the lowest risk of mortality. And then in extremely hot days, there's a higher risk. That's the heat mortality risk. And also at colder days, there's additional risk as well. But you can see that these curves are very different, and these relationships between temperature and mortality are very different from city to city. And so that raises the question, well, if there's such differences across different cities and how temperatures impact health, wouldn't those differences also be within cities at the neighborhood level or at other smaller areas? If we have pockets of heat in certain neighborhoods and also pockets of social vulnerability, would those neighborhoods be at higher risk from heat than neighborhoods that, for example, are cooler and where people have more resources for air conditioning or things like that? So these next two projects really try to get at this neighborhood level or the smaller area level than just the city level to try to understand these smaller scale disparities in the effects of heat, which also hopefully will give us information on how we can design neighborhoods and protect populations from the health effects of heat. And so when we break this problem down, when we think about, okay, what is it that creates higher risk in some neighborhoods and lower risk in other neighborhoods, we think about two major factors. First, we think about exposure. So this is differences in which neighborhoods are hot and which neighborhoods are less hot, which neighborhoods are cooler. And we can think about factors like the built environment or green space, for example, that might determine which neighborhoods are experiencing hotter temperature exposures and which neighborhoods are experiencing lower temperature exposures. And then we can also think about vulnerability. So this is things like related to the neighborhood's social environment. So you think about resources such as access to air conditioning, access to cooling centers, or even physical characteristics like underlying chronic disease that may make one neighborhood at higher risk for experiencing health effects from heat compared to another neighborhood. So today we're going to focus on two different studies. In the first study, we're going to think about heterogeneity in the impacts of heat on mortality in neighborhoods of several cities of the Americas, So this will really help us understand how different are these risks of heat on health from neighborhood to neighborhood within the same city. Are most of the neighborhoods similar, or are there wide disparities between neighborhoods within the same city? And the second study is to identify neighborhood modifiers of the effect of heat. So this tells us, well, what are the features of that neighborhood that may be contributing to these differences in heat mortality risk? And this, of course, helps us understand how we can design neighborhoods in the future going forward to protect the population from the health effects of heat. And then throughout both of these projects that we're going to present here, we have two kind of underlying threads that go throughout the research. First is thinking about continuous policy engagement and how policy can inform research and research can inform policy. And second, thinking about how building a data infrastructure can bring together diverse sets of data from different sources to generate useful evidence on these questions. Over to you, Usama.
Thank you, Josiah. So, as Anna mentioned before, this is part of the research project um, that is done from the Drexel Research Center on Extreme Weather and Urban Health, which is a center funded by NIMHD as part of the P20 Centers for Health and Extreme Weather. The center has a few more days left, around 10 days left. I hope to continue this kind of work, and the objective was always to be linking things, the connection between extreme weather and urban health across cities of the Americas. Next. So one of the key aspects of this center was the creation of a robust data infrastructure that actually allows us to work in this kind of research. And this is a schematic. It's not meant to be detailed here in the sense that shouldn't be reading each of the little small boxes here. But what I want to highlight here is that as part of this data infrastructure, we are able to ingest sources related to weather data, sources related to health data, and sources related to social factors, environmental factors, and population and boundaries. All of that goes to a centralized data warehouse where all of this data is combined, clean, and arranged in a way that is useful for all of the analysis that we are going to be showing today. And eventually, we have a list of manuscripts, out of which today we'll be presenting two of them. And these manuscripts plus all of this data ends up resulting in analytic data sets that allow us to do uh, research in a much more re reproducible way. So next slide, please. So the basic design across all of the two studies that we're going to be showing today is around the metropolitan areas of 5 cities across the Americas. These cities are different in terms of size, from around 2 to around 20 million. Climate, so some of them are tropical, subtropical, and temperate, and also as a result, differences in temperature. They also have different shapes of the temperature mortality curves. The one that Josiah showed before, they are radically different, and we'll see how that creates some issue with our research. And they have, in general, different segregation patterns. These you will see in a lot more detail when Josiah presents the second study. But this actually is a great advantage of comparing cities across multiple places because they allow us to leverage all of these differences. Next slide. So the two studies we'll be presenting today will be focused on both Philadelphia and the 4 cities in Latin America, which are Rio de Janeiro, São Paulo, Guatemala City, and Panama City. We'll be presenting a study on heterogeneity and a study on modifiers, and then we'll be talking a little bit about the engagement we have done to make these results a lot more relevant. Next. So in terms of statistical and data design in general, we are linking daily all-cause mortality to city level mean or average temperature. Then we are using time stratified case crossover design with a time series implementation. These are time stratified by day of week, month, and year in order to address both day of week effects, but also seasonality and long-term trends. And our exposure response function is modeled using a distributed lag nonlinear model. In the case of the summer findings that you will see, especially with nonlinear temperature nodes at the 75th and 90th percentile, and then delayed effects up to a 7-day lag with 2 nodes, some of these being quite standard settings for this kind of model. So for study 1, on the heterogeneity, the main challenge we have is that we are dealing with small areas. Most of the research on this topic tends to focus on cities, which are, relatively large, hundreds of thousands, millions of people. Here we are dealing with neighborhoods. And in our case, they hover around 30,000, especially in Philadelphia and Brazilian cities, around 50,000 in Panama, and around 100,000 in Guatemala City. So they are small areas, which means that they have small death counts. And a small death count leads to statistical instability, so then we'll get a lot of noise. So in order to address this, we leverage a new technique called spatial Bayesian distributed lag in nonlinear models, which essentially smooth the relationship between temperature and mortality towards the neighborhoods around each of the neighborhoods that we are looking at, with the idea that there is something similar about a neighborhood and everything that surrounds it. So what we are going to be showing now in this first study are temperature, mortality, exposure, response functions by neighborhood, and the maps of how that looks like comparing extreme heat, defined as the 99th percentile. Think of that as the 3 hottest days of the year, versus the 75th percentile of temperature, which tend to be the temperature at which mortality is the lowest. And then we'll also show maps of significance, kind of statistical significance of the probability of that rate ratio to be above 1. Next. But before I show you results, I want to show you what happened when we actually showed these results to stakeholders as part of the work we do with the community engagement core of the center. So we showed what's on the left, which is essentially a map of the metropolitan area of Philadelphia. And Philadelphia is actually a teeny tiny part in the middle of all of that, around there. And then everything else is the suburban counties around Philadelphia. And we also showed the exposure response function, saying, look, there's a lot of variability here. And we do this, and we do this a lot in our research, because cities don't really stop at the administrative borders, like cities continue spreading out. This also gives us more variability in terms of features of these areas, and it also gives us more sample size. We like more sample size. But what happened is that when we presented this to stakeholders in the city, the Department of Public Health and the Office of Sustainability, that does some of the resiliency planning around extreme weather, they said that the jurisdiction is the city. Well, that's what we care about. It's nice saying what's happening outside of it, but we want to focus a little bit more on the city. So then we went back to the drawing board and started showing city-specific results. So in this case, what we are showing here on this figure will be the part of that is around that red circle on the left there, and the curves that we are showing here on this graph will be the ones specific to the city. Next. So to summarize, these are the findings that we found in Philadelphia and showed the other cities, but I wanted to start with Philadelphia neighborhoods here. We found that the impacts of heat were widely heterogeneous. So the red line that you can see around 30 degrees Celsius is that consider the extreme heat here. Remember, this is average daily temperature. It's not the max temperature. That's why it doesn't look that high compared to max temperature that we have seen the last few days, actually, where we were up to 35 Celsius. So we are comparing that to the 75th percentile, which falls around here, around 26 Celsius. And essentially, everything you're going to be showing in the following maps is a comparison on where each curve is in the 99th versus where each curve is on the 75th percentile. And what we found here is that the increase in mortality in those extreme hot days hovers from around no increase, which are these neighborhoods here, to around a 17% higher mortality risk. So we found a big difference between neighborhoods in the city. Next. Now, we showed that same amount, the 99th versus 75th percentile in a map. That's what you get on the map on the left here. And what we see, first of all, is a spatial patterning here. So the southwest of the city has much higher increases in mortality with extreme heat compared to, for example, the northeast part of the city. The map on the right shows a measure of statistical significance. This is not exactly the same thing, but what it shows us is the areas where we are quite certain that there is increases in mortality with extreme heat, and allow us to categorize this map a little bit more. And as you can see, it's again those same areas in Southwest and in West Philadelphia and some areas in North Philadelphia. Next. Now, what happens if we look at all of the other cities in the project? Well, first of all, the two cities of Brazil are on the right, and what you see there is somewhat a similar pattern that what we saw in Philadelphia. An increase in mortality with extreme heat and a somewhat wide variability. Note that the y-axis here is very different compared to the prior one. So actually in Rio, mortality on extremely hot days goes from around 15% in the neighborhood with the lowest increases to around 50% more in the neighborhood with the highest increases. So a lot of variability there, even if it doesn't look that much here. The other thing I will say here is the two cities on the left, Guatemala City and Panama City, have barely any effects. They are quite flat. And actually, in some of them, it almost looks like in the hotter days, according to each of the cities, mortality goes down. What I want to point out here is that the x-axis are very different. So you can see anything on this graph, because if we go to the following slide, where we put everything on the same axis, you can see that the distribution of temperature is very different. And we think this is one of the reasons why we are not observing effects here. In Guatemala City, it never gets that hot. So the 99th percentile is around 23 Celsius. And in Panama City, the problem is the opposite. We don't have anything on the cool side. So there is really not a comparison there. So we didn't find much in these cities. We think that different methods are needed to study mortality in cities that don't have this distribution of temperature. Next. Now back to the framework that Josiah showed before. What we are seeing here essentially is how city level temperature has a different causes a different temperature related mortality depending on the neighborhood that you live. Now, this could be because neighborhoods have different exposure to temperature. Some neighborhoods are hotter, so the same city level temperature leads to different neighborhood level temperature. Or it could be because the people in those neighborhoods, or because of the feature of those neighborhoods, the impacts of that temperature varies a lot. Now, which one is it? From what we showed, we cannot really tell. So in another aim of this project that we are still working on, we are trying to decompose this, to decompose differential exposure to temperature and the differential effect of temperature. And I just want to give you a little bit of a sense of how we are going to be doing this. We are currently doing this kind of analysis now. So if we think of the excessive death fraction as a measure of how much that temperature mortality curve, you multiply it with by the actual distribution of temperature, and it gives us what proportion of deaths are attributable to temperature, either heat or cold. So if we think about heat, and we want to see what is the disparity in EDFs in each neighborhood, so how different is each neighborhood, in this case EDFI, to the city, in this case EDFC, we can decompose this into components. One component that is due to different neighborhoods having different temperatures, and another second component about different neighborhoods having different responses to temperature. So in the case of the first part here, the difference in the temperature, the way we are calculating that is by on the one end estimating what is the actual impact of the temperature that neighborhood has on the mortality of that neighborhood, and on the other side, subtracting from that, what would have been the effect in that neighborhood had the neighborhood had the city level temperature. So we are removing the city level effect and just keeping the neighborhood level effect of temperature. And on the right here, with the differences in the effects, what we do is compare that. What is the city level temperature? What will have been the effect with city level temperature, and subtract from that what is the effect in the overall city, leaving only the effect because of differential effects. We don't have results on this yet, but we think this is a promising development that we hope to be able to share soon. Josiah, I think you're next.
So Usama just talked about trying to quantify how much variability there is between neighborhoods and heat risk, finding there's quite a lot of variability between neighborhood to neighborhood within the same cities. And then the second part tries to look at, well, what are the features of those neighborhoods that have higher risk versus lower risk, hoping to provide evidence on what exactly maybe could be intervened upon to reduce risk in those highest risk neighborhoods. And so in this paper, we're looking at different small area or neighborhood modifiers of this heat mortality association across these same 5 cities that Usama just presented. So the modifiers we're looking at in this paper are neighborhood green space, and we're thinking of that as just one proxy for higher exposure, of course, because more green neighborhoods tend to be cooler because there's less of an urban heat island effect, and neighborhoods that don't have much green space tend to be hotter. We're also looking at neighborhood education as a proxy for socioeconomic status more broadly at the area level, not the individual level, but at the area level. And we're using this as a proxy to try to get at neighborhood vulnerability, social vulnerability that may be related to their risk from experiencing health impacts from heat. Now, the challenge is if you think about a city, which neighborhoods have green space and which neighborhoods have high or low education can often be very correlated. And so if we just look at one factor at a time, which is what is most common in the scientific literature, there may be confounding by the other factor. We may not know exactly which factor is really driving this association. And so our approach here is to create 4 different neighborhood profiles. So by doing this, we're creating 4 different categories of neighborhood based on low or high green space and low or high education. So that's, of course, low green space, low education, low green space, high education, and so on. Then we use the same modeling approach, a similar modeling approach that Usama mentioned, the case time series design, but we're stratifying by each of these 4 neighborhood profiles to understand what is heat-related risk in this one neighborhood profile type compared to another neighborhood type. And really importantly, in this process, we're adjusting for age. So that means that just because there are more deaths among, say, older adults or younger people who may be more or less vulnerable, that is controlled for in this analysis. But with the goal being to really try to understand this independent and joint effect of green space and education on determining neighborhood risk. Now, I mentioned this correlation between green space and education. And one really interesting thing that we found that we were able to learn from looking at these 5 different cities is that there's actually opposite correlation between green space and education in these cities compared to the other. So in Philadelphia, for example, there's a positive correlation between green space and education, meaning that more green neighborhoods tend to have higher education. So you could think of this as sort of wealthy suburbs, for example. Lots of green space, higher education. However, in the 4 Latin American cities, we found the reverse. We found higher green space in low education neighborhoods. So there's a negative correlation here. And in this scenario, the higher education neighborhoods tend to be concentrated in the urban core or other more central areas that have actually less green space than the lower education periphery. So by comparing these 5 different cities, we can really learn a lot about how these features work differently in different places. So this is just some maps to give you an example here of the 4 neighborhood profile approach. So in the darker brown here, you have low green, low education neighborhoods. So let's just zoom in on Philadelphia here on the top left, for example. So these darker brown, low green, low education neighborhoods tend to be clustered within the urban core or within Philadelphia city proper. Meanwhile, there's this band of the dark green, which is the high green, high education neighborhoods. These are sort of the relatively wealthy suburbs here. So you see this low green, low education urban core surrounded by this high green, high education suburbs. But this pattern is not the same for all of these cities. If you look at São Paulo, for example, in the bottom left, you see that the urban core is actually low green space and high education. That's that tan color. And so you can see that in each of these cities, there's different joint distributions of green space and of area level education. So which is the most important factor for driving or determining which neighborhoods have heat risk? Or are both of these factors important? So to do this, we ran these analyses of understanding heat mortality within each of these 4 different neighborhood profiles within each of these cities. So again, to hone in on Philadelphia, for example, you can see that in these high green, high education neighborhoods, there's really not much extreme heat risk. So during a 99th percentile hot day compared to a 95th percentile hot day, we don't actually observe an increase in mortality in those high green, high education, sort of relatively wealthy suburban small areas or neighborhoods. In contrast, in these low green space, low education neighborhoods in the urban core, and many of which are within Philadelphia proper, we see this much higher risk of mortality under these extreme heat conditions. Now, this is different in Rio de Janeiro and São Paulo, where we see elevated heat risk among all of the different neighborhood profiles, but to different magnitudes, right? In each of these neighborhoods, these low green space, low education neighborhoods tend to have the highest heat-related risk, and the high green space, high education, or best case scenario, tend to have the lowest risk. Now we can compare the relative risk from these neighborhoods with each other within the same city using this high green space, high education neighborhood as the so-called best case scenario. So you have a lot of green space that keeps it cool, and you have high area level SES, which hopefully means you have more resources to protect yourself from the heat. And we can compare the risk during extreme heat with using this as the reference group with the other combinations of education and green space. And what we find overall is that there's this special, especially in Philadelphia, there's this special unique profile of this double threat of low green space and low education that makes the risk of heat-related mortality especially high. So all of this research, how do we do it? We talked at the beginning about trying to integrate this research with community and with policymakers. So I'm going to just describe briefly a few different ways that we've been able to engage with policymakers and decision makers related to this research. So I'm going to quickly talk about some meetings, some discussions we've had with the Philadelphia Department of Public Health, with ICLE, which is an organization that works with local governments in Latin America related to sustainability, with the C40 Cities Climate Leadership Group, who connected us specifically with city governance departments in Rio de Janeiro and São Paulo. So how our engagement shaped the research in Philadelphia? Usama mentioned this briefly before. So we presented these metropolitan level results to the Office of Sustainability in the Health Department, and they said, this makes sense, first of all. And that's important to kind of ground truth or get a gut check that what our statistical models are telling us reflect the reality on the ground. However, as Usama mentioned, these policymakers from the city of Philadelphia said, the metropolitan area is not our jurisdiction. Our job is to take care of people in the city, and we need city-level results. So we reran these analyses just within the municipality of Philadelphia City, and we're able to produce kind of a parallel set of results just for the Philadelphia City proper, which the city is now using and incorporating into their heat vulnerability assessment. So we presented these findings to the Office of Sustainability Resilience Working Group, and we were also able to provide some expert review of the city's heat vulnerability assessment. Now, in this, we came across kind of an interesting conundrum in working with the city, which we still haven't fully resolved. And one is that, on the one hand, city policymakers wanted to be able to cite our work, of course, as a peer-reviewed academic source to justify the policy decisions that they're making. However, they also need the results very soon. And so, of course, the academic publication process can take a long time, 6 months or even a year. And so trying to balance getting results soon that can be very responsive to the immediate needs of the city with also being able to provide very scientifically robust and peer-reviewed evidence that can be the support for these policy decisions. Next, I want to highlight our partnership with the C40 cities. So C40 facilitated meetings that brought together health departments and planning departments in Rio de Janeiro and São Paulo. And so we met with these joint, Rio Health Department and Rio Planning Department, São Paulo Health, São Paulo Planning. We presented these results to them, and we're able to have very informative and interesting conversations about what they're doing with their work now and how our research can inform or be responsive to their needs. We found very different things. In Rio, they had a very well-developed early warning system. The health department was very involved, whereas in São Paulo, they were much earlier in the process of developing their heat action strategies. But it was very helpful and insightful conversations, both to inform our future steps as well as hopefully to provide evidence to inform their planning. So overall, wrapping up, our scientific takeaways of the two studies that we presented are, first of all, heat impacts are very heterogeneous within cities. Second, these modifiers, specifically education and green space, can really vary in how they're distributed within the city and how they overlap with each other, depending on what the city is. So you can't just look at one and assume a constant correlation with the other. Third, education and green space appear to be independent drivers of neighborhood heat health risk. And intervening on either of those factors, again, thinking of these as proxies for the larger socioeconomic conditions and larger built environment related to temperature exposure, could be ways to protect high-risk neighborhoods from the health impacts of heat. And lastly, we found some evidence of a potential kind of synergistic or interactive threat in these low green space, low SES neighborhoods, which seem to be the number one neighborhoods that policymakers should target if they're thinking about heat health interventions. And then lastly, throughout this project, we've learned city scale data are essential, and aligning the research to the level of where the decision making and the policy making is taking place is really important. Metro level analyses may make more sense from our scientific perspective, but city policymakers need something that matches with their level of governance. Second, engagement can drive scientific questions and make this scientific evidence more relevant, which is very important. And then lastly, building this data infrastructure really pays off in the long term from a research perspective, because it allows us to create a lot of different related research projects building on a shared common evidence foundation and data foundation. Thank you very much.
Thank you. Thank you so much, Usama and Josiah. Very, very interesting work, and it's great to see the integration between the research and the policy engagement and impact, which was really a major component and goal of the center. So thank you so much for sharing that as well. So you can put your questions in the Q&A, but you can also ask your questions, I believe, if you would prefer. I see Carlos Valencia with your hand up. Do you want to introduce yourself and ask your question?
Hi, Usama and Josiah. Thank you for your presentation. It was very interesting. I'm Carlos Valencia, Assistant Professor of Epidemiology at the Universidad de los Andes in Bogota. I work with Olga Lucia. And my question was like more towards the end about what you described was like the transition between like your findings and like the policy recommendations. And well, you know, as you mentioned, it's kind of tricky sometimes to kind of work with stakeholders and policymakers when they ask like, okay, but what could we do, or what changes could we do, or like what do we recommend to like people or the population in general? So I don't know if you have like a hint on like how to like bring down like those kind of what they could see as abstract kind of numbers to like specific policy recommendations.
Thank you, Carlos. I'll start with something, and then Josiah, please feel free to chime in. Um, my first answer is that a lot of what we have shown helps us see where we have to do something, where something needs to happen, right? Less so what and more the where, right? And I think that was always a goal of this, saying, you already know what to do. I'm going to tell you which areas you have to prioritize for this, because of course, every place has limited resources and they need to decide what to do. And here we are saying, look, in the case of Philadelphia, that southwest area really needs some work in terms of, you already know, in terms of either greening, outreach, etc., etc. There are many things that could be happening. Josiah, I think, will talk a lot more about those. But here is a lot about targeting. And we have another aim where we are trying to target in population subgroups. We are not talking about that one yet. It isn't ready to be shown. But in this case, it's more okay, these are the areas that really need work. Josiah, I don't know if you have any thoughts on what work these areas could actually use.
Yeah. Well, thank you, Carlos. What comes to mind for me is thinking about it was so beneficial for us to meet with policymakers in Philadelphia, for example, earlier on in our process. So this is before we've written the papers, before we've published the papers. And it really has helped us think about what they're thinking about and what questions they need answered. And so, for example, in the work that Usama and I have done with the city's heat vulnerability assessment, we now have a better understanding of the interventions that they're considering, which we can then perhaps provide some more evidence on. And so I think my main takeaway is having that early interaction with them is can be way more valuable than if we had waited later until after our project and we did what we thought was useful was over. Yeah.
Thank you. We have a question in the chat in Portuguese from Thaisa Lucas. I think if I'll take a stab. I don't know if I'll be able to translate, but I'll do my best. I believe Thaisa wants to understand the source of the meteorologic data and the temporal and spatial resolution of that data.
Yep. So this is two different sources, both reanalysis data or model data, depending on which one. So for the Latin American cities, we are using ERA 5 land with a few post-processing things to make it um, population weighted. This is daily average temperature, and the resolution of ERA 5 is 9 by 5 kilometers. So it's a good representation of the city. These are relatively big cities. In the case of the Philadelphia area, while we could be using that, and actually probably something we'll need to consider is a sensitivity analysis using that same source of data. In the case of Philadelphia, we use PRISM, which is a reanalysis and model data set by the University of Oregon that is actually a lot more geographically detailed. It has 800 by 800 meters. And we chose it because we want to use it eventually for that second decomposition thing where we need neighborhood level temperature. In any case, it is also daily average temperature. Josiah, I hope that I may have jumped too fast on your side of things. But
No, 9 by 9 kilometers. Yep.
yeah.
Thank you. Other questions? You can put them in the Q&A or raise your hand. While we wait to see if there are any other questions or comments, I had one question on if I understood correctly, the analyses that you showed are restricted to the warm months. Is that right? I hadn't realized this before, and I'm just curious if that's the case, why you did it, and if there are any implications
Yeah.
of that.
When I started saying that, I realized that I meant that only for the first project, the Bayesian one.
Uh-huh.
The reason why we are doing that in that one is because we wanted to limit the number of coefficients we need to estimate.
Uh-huh.
So by doing that, we could do one fewer not for the lags and one fewer not for temperature. And that results in a saving of around 8 coefficients, which results in a lot more computational efficiency. Josiah, I believe that yours still uses the regular all year, right?
Yes, for the modification analysis, it's all year.
Okay, thank
We
you.
still show percentile 99 versus 75th in both, but the way we get to that is a little bit different.
Yeah. Is there any, I don't know, Josiah, this might be a question for you. Why do sometimes people do this, restricting to the warmer months, or do you have any opinion on this, I guess?
Well, if you're only interested in heat, so it's very interesting to think about cold. It's very important. But if you're only interested in heat, it can cut down your data set, which makes it much quicker to process because some of these models can be very computationally intense. And can also make the modeling easier because, if you look at the whole temperature range, usually you have this nonlinear U-shaped curve that can be complicated to model. But if you only focus on, the extremely hot months, you get something closer to a linear relationship sometimes because you're only looking at half of that U. So depending on what model you use, it can just be simpler.
Mm-hmm. Thank you. Carlos, do you have another question? Go ahead.
Yeah, thank you. Could you please expand a bit on the challenge of modeling within those small areas and with that small number of events, what was kind of the biggest like hurdle like on the analysis, and like if you have any advice for those situations?
Yeah, great question. We've struggled with that for the last 2 years. So originally, what we wanted to do here was model similar to how people have been modeling this when they look at cities, right? It's normally a first stage where you model each city separately, and a second stage where you smooth those using certain variables. And that's usually called a two-stage meta regression. That's the summary of that. Now, that works very well when you have big cities and therefore a lot of deaths. It works quite well when you have smaller cities, but here we're talking about small, even smaller neighborhoods, right? So there is a lot of statistical noise because there aren't that many deaths. So right as we were starting this paper by Quijal Zamorano and others came out proposing the spatial Bayesian approach. In the first paper, they are doing that with a classical Bayesian implementation, which uses resampling and a lot of complicated Bayesian things. In our case, the time to run the model for a single city, Philadelphia, which is in the middle in terms of size, so if we do this in Rio and in São Paulo, it will take longer. It took around 2 weeks to run that model in a very powerful computer. Very frustratingly, in the first time we were about to finish that, we had to move offices. So I had to stop the model at the 13th day. And I remember the last day I was saying, no, no, please finish. And then I said, well, I need to leave. So I guess I'll have to restart it. So I restarted it in the other place and took another 2 cities. And then a few weeks after that, the same authors came up with a different implementation using INLA. So INLA is a method that doesn't use the full Bayesian resampling or sampling, but rather uses approximations. And they showed that the model fits quite similarly. And actually, we did a test with a smaller sample, and we found that the results were very similar. It takes 20 minutes to run. So from 2 weeks to around 20 minutes. And that's, again, with a very powerful computer. If we are talking about a powerful desktop computer, if you try to do this in a laptop, I don't know if it will survive all of this. So from then on, we've been doing all of this with INLA. And actually, I mentioned before that we do the warm months because of computational efficiency. We've gotten to the point where we have tweaked the model enough that we think we are ready to do the whole year now. But again, these are models that are very new. We are talking about papers from the last year or 2 years ago. So hopefully more efficiency is coming through so that these models are more accessible.
I'll
Thank you.
just
Yeah, go ahead.
I'll just add one more thing about that is, you know, when in the modification analysis, we have the neighborhood split into only 4 groups. It would be great to be able to expand that and have more nuance. But the reality is when we're cutting the city into 4 parts, we really lose a lot of certainty, a lot of power. And so it's definitely a challenge, but it also impacts the questions that we can really answer.
Thank you. There's another question in the chat from Kai. Can you please briefly explain how the RERI is calculated? I initially thought it involved just dividing one relative risk by another, but now I'm wondering how the confidence interval is determined.
Great question, Kai. This was a last minute thing I did before a prior presentation, so I hope I can explain it well. So when you think about effect modification or interaction, either one, in this case, we can think of it in absolute or in relative. Sorry, in absolute, in relative terms or in absolute terms. And actually, Josiah, if you share that slide again, I can maybe explain that. So there are in terms of relative measures, that's your typical ratio of rate ratios. So that's what actually you see on the right here. That's what you see exactly here. And in the case of the ratio of rate ratios for Philadelphia, that's around 1.21, I think. So that's what you see here. The area is different. So the ratio of rate ratios essentially tells you what is the relative increase in mortality comparing, in this case, low green, low education versus high green and high education. And if you are doing this in a model, that's just the exponentiated interaction coefficient. The REII is a little bit different because the REII is a measure of additive interaction, so it plays in absolute terms, and it takes into consideration that the baseline risks are different. That, for example, in Rio here, the baseline risk by baseline, I mean in this case the group that has the lowest risk is much higher than in Sao Paulo, for example. So the REII takes that into consideration. And the way you calculate an REII is that essentially you take the risks in the group that you are interested in the combination group, in this case low green and low education, and you subtract from it the effect in one of the groups that has one of the variables, the effect in the group that has one of the other variables, and the effect in the group that has neither. So essentially, what you are trying to see here is how much extra risk is conferred by adding the two things. The two exposures together, and it's a measure of additive interaction. Now, the interpretability of this measure is always tricky. That always happens with REIs. It's the specific numbering itself is always hard to interpret. But think of it as if you add the two exposures together, how much, how literally how many more points of relative risk you have in those areas. We haven't calculated the confidence interval here for it. That's why we are not showing it, but we could. There are formulas to use a delta approximation to do this, or there are other ways to actually look at this. But yeah, that's a great question. Thank you.
Thank you. Any other questions or?
I see a question on the Bayesian model in the chat asking if the Bayesian model is considered the spatial structure of the data. Is it a spatial Bayesian model? Yes, it is a spatial Bayesian distributed like nonlinear model, where essentially the coefficients for each neighborhood that form the curve for each neighborhood, they are smooth towards neighborhoods around it. And the idea is that neighborhoods around it are more similar in terms of both exposure and vulnerability, and that's why we leverage that spatial structure. And we use a queen contiguity, for those of you interested in that, meaning we use all neighborhoods around it.
Okay, any other questions? Mariana, go ahead.
Yes, very nice presentation. I have a question about the temperature. You use city level temperature. How common and how useful for the type of research questions that you are asking here? Would it be to have more local neighborhood level or a smaller scale temperature information? How would you use it, and how common is it? Is it something that would it be feasible, in the future?
Yeah, thanks, Mariana. So in this analysis, we use city level temperature, which means that when we're looking at differences in the neighborhood health impacts, we're kind of incorporating together any differences in neighborhood temperature and exposure and in vulnerability. So we're looking at both of those combined together. If we were able to use neighborhood level temperature, it would help us to really isolate what is temperature versus what is vulnerability. And so what we presented today is kind of a first stage of the analysis where we look at these two things together. And then we hope that in the future, we're able to do more analyses with the neighborhood level temperature. The big challenge is for the Latin America cities, we just don't have temperature data available at a fine spatial scale. So the data set that we're using is really the best that's available. It's around 9 or 10 kilometer grid cells. And that's not really fine enough to really get at these neighborhood level differences. So we're doing the best we can with the city level data. In some cities, we've been part of creating these much more finer temperature resolution data, but it's expensive. It's its own project. It's not something that has been done globally or that we could do easily for a large number of cities. Meanwhile, in the US, we do have that fine resolution data. And so the analyses that Usama talked about, where we actually look at neighborhood temperature differences, are because we have that data available at a finer spatial resolution in the US. So it's really a limitation of the data, but we're still able to answer some interesting questions with it.
My sense is that this is going to change. I see more and more models in the US for this. Like different groups are actually producing different models. As soon as that, I think, gets extended to other areas, I think we'll start having this more readily available. There have been already some efforts that include Latin America, but if you look at them, we're not so convinced about the quality of that modeling effort. And then, as Josiah said, we actually have another project where we are trying to do that in 2 different cities. It takes months to run some of the models that we tried using in those, because they are very physics-oriented models, while the new trend of models are more machine learning things that leverage less physics-oriented models and more prediction.
I would say this is a rapidly developing field, and I would expect that in 5 years from now, we have global data at a much higher temperature resolution.
Mhm. There's another question in the chat. Can you guys see it?
Yes. How to use this methodology for a municipality with 330 square kilometers, with high variability in altitude, and 480 neighborhoods. And what methodology do you mean in all of these things? And we've shown a little bit of a variability here.
Is it the temperature estimation or is it the temperature impact on health piece? I guess that would be the first question, Thaisa.
I'll just say I think this is a great challenge. In this city level data, if there's a lot of variation in altitude, that of course would mean a lot of variation in temperature,
Right.
especially in these temperature ranges here, these wide temperature ranges here that you're referring to. So that would be even more challenging to use the city level data, I would guess, because it would really be even harder to capture the wide variability that you'd expect in neighborhood temperature.
Mhm.
That being said, Josiah, there is also the argument that city-level data was used for deciding things, right, at the city level. So there is an argument for city-level temperature being more useful from an intervention perspective, city-level intervention.
Right. And I think
Yeah.
that ties back to what we were talking about. Oh, you shouldn't just do it at metropolitan level. You have to do it at the level where the decisions are made. In the same way, it could make sense to redo this with the exposure metrics that are being used by the local decision makers for heat action, heat alerts, and things like that.
Well, on that note, I think we're almost out of time. So I want to thank Josiah and Usama again for the great work and a great presentation, a great final presentation for our center. And hope this will not be the final one. And we'll be back with you soon. And thanks everybody for joining. And we'll be in touch. Thank you.
Thank you.